Good afternoon, everyone. Welcome to Taco Tuesday, commercial focused style. Brett Zerba here, and I am actually sitting in the what we call the Fresno room at Taco's classroom in Cranston, Rhode Island.
Why did they pick Fresno, Brett?
What's that?
Why did they pick Fresno?
Because that's where we built one of our new facilities for our vertical turbines out in California.
Oh, isn't that? Well, I knew it was in California, but I didn't realize it was in Fresno. So that's kind of neat, huh?
Yep. But I mean, Taco has really expanded quite a bit the past few years, and we built two new facilities for our vertical turbine division. One in Lubbock, Texas, and another one in Fresno, California. Good afternoon or good morning to Paul from Fairbanks. I'm assuming it's morning in Fairbanks. What do you think, Rich? If it's Fairbanks, Alaska, he's having his second cup of coffee because he's just waking up.
All the way from Fairbanks, Alaska. Holy mackerel!
And we got Eugene from Anchorage. 8 a.m. Paul says it's just after 8 a.m. So
what's the temperature? What's it like out there this time of year? Well, Fairbanks is colder than Anchorage, isn't it?
Yeah, it's further north. I know it was minus. It was minus.
Your audio is breaking up.
Am I? All right.
Yeah.
Well, let's get going. Brett with Taco. There are two handouts. It sounds like people can hear us. Can you hear me all right, Rich, or am I breaking up still?
I can hear you now perfectly.
All right. I'll try not to move around as much. Eugene says it's 40 and sunny. I don't know if that Eugene, and he's in Anchorage. That's not too bad. Anytime it's sunny, that's a good thing.
Anytime it's above freezing in Alaska, that's a good day.
There you go. Bob Mendez, new hire here at Taco. Robert Mendez from Taco. We got a new hire on. Oh boy, Rich, we're under pressure. We're under pressure.
Oh, we
Paul
are?
says, Paul from Fairbanks says it's 38 and he's on his third cup.
Holy mackerel. So how long is let's ask Bob Menendez, right? Oh no, Bob Mendez, not Menendez. Mendez.
Yep.
So how long have you been with Taco, Bob?
He'll type that in. Anyways, like I said, while we're waiting, there is two handouts. One is the slides that Rich is going to talk about, and I'll let Rich tell you what the other handout is after you download it. But it is part of the presentation as well. So Thermal Appliance Company started in 1920. My fourth week here in tech services. We'll be dealing with him. He's up with Mario's, the two Marios, and Steve. I think he works for Steve. John Levely. Yeah, a bunch of people up there. Tom.
Nice.
And then that part-timer that retired that can't leave. He bumps in every once in a while. Drewski.
I haven't seen Drew since he retired. So he comes back periodically and says hello?
Periodically, yeah. So
nice.
Rich and I are having a conversation and with other people, and you know what? We're going to get into this presentation. NPSH. And I tell you, I hope nobody on this call, which I doubt, has ever had an NPSH issue on their project. Pay attention today so you never have one, because when you do, it could get very, very expensive for somebody. And I don't need to get into too many details, but every once in a while it happens, and it's a pain when it does. That's all I can say. So, anyways, NPSH, Rich, take it away.
Well, good morning, or actually it's afternoon because it's after noontime here in the East Coast. So good afternoon, everyone, and thank you for joining our Taco Tuesday presentation on the introduction to net positive suction head, abbreviated NPSH. So we're going to cover a couple of different things. First, we're going to talk a little bit. We're not going to talk about anything, Brett, because the damn computer isn't working again. Let's try it one more time. There it goes.
Woo. Hallelujah.
Woo. I know it. So what is NPSH? I like to talk briefly about the Goldilocks planet, how to find net positive suction head required. NPSHR stands for net positive suction head required. And then also properties of water vapor. And then we're going to also figure out how to calculate the net positive suction head available available. So we have two types of NPSH, one required and the other one available. And then we'll have a short discussion at the end. So,
Hey, Rich,
yes,
can I interrupt for a second? Because I forgot to
absolutely.
say this. Brett Zerba is very, very happy again today because Sunday night, just after 9 o'clock, my daughter had a son,
Had another baby.
Jackson Michael Tebow, seven
Excellent.
pounds 9 ounces, and I am going to go.
Holy
Don't
mackerel.
tell anybody in the world. Don't tell anybody. I'm going to see him very, very shortly. So
We'll keep it a
you
secret.
ask as many questions as you want, but at 1 o'clock, this session's over. back, back to you, Rich.
Okay, so what is NPSH? So I have the definition up here on the screen, net positive suction head, and here's the actual definition. I'm going to leave it up there for a moment so that you can either cut and paste that, or if you get the rebroadcast. The rebroadcast is what, tomorrow, Brett? 24
Yeah,
hours roughly from
they all
tonight?
have the slides too, Rich, if they want them.
Yeah, so I don't like to read things online, I mean, on a broadcast. So there it is. You can see it and you can read it if you download it and all that other kind of fun stuff. All right, so what do we mean by the Goldilocks planet? Well, you've probably heard the story about Goldilocks. I remember, by the way, I asked a live class several years ago. I said, can someone tell me the story about Goldilocks? And this one person raised their hand and they said, well, Goldilocks was running through the woods with a red, what do you call that? A red hood. And the wolf tried to capture her. And I said, no, that's Little Red Riding Hood, not Goldilocks. So Goldilocks, again, Goldilocks was this person that was, I don't know why she was running in the woods, but she was in the woods somewhere and she came across this house in the woods. And she went inside and there was, I guess it was porridge was the first thing she came across. And one was too hot, and the other one was too cold, and the third one was just right. So, by the way, it always bothered me because here's this Goldilocks person running around the woods, breaking and entering into this bear's house. That didn't seem appropriate. But anyway, the point is that when we refer to the Goldilocks planet, it means that it has the temperature is not too hot, it's not too cold. In other words, the temperature is just right. And for our discussion today, not only is our planet, Earth is considered a Goldilocks planet, it's also the pressure is just right. So it's not too hot, it's not too cold, the pressure is just right. And that means that our planet has, for I think roughly 70% of the Earth's surface is covered by water. Actually, it's a little bit less than that because we have the Arctic ice cap, and then we have the Antarctica. But anyway, so one of the things that we're going to be talking about today is water and the fact that water is not too hot, not too cold, and the pressure is just right. Okay. So how do we find net positive suction head required by a pump? Well, here is a picture of a pump curve. And if you'll notice, let's see if I can draw on here. Let's see if my pen works, Brett. Is my pen working right now?
It is.
Oh, look at that. That looks good. Okay, so if you'll notice, this is a nice pump curve. This red line represents the pump curve. The blue line represents the system curve. And if you'll notice, if I kind of jot down, actually, I'm going to get a straight edge here. I've got a straight edge sitting in my desk drawer. If I draw a straight edge here, just kind of dotted line here for a moment, you'll see that that is approximately 2,400 gallons per minute. And if I extend that line vertically upward, you can see where it intersects up here. Can I draw kind of a little cloud around that? You can see where it intersects the top chart here. If I draw a vertical line from my 2,400 gallons per minute, and it intersects this nice curved line up here called the required NPSH. So that's where you find the net positive suction head required for a pump. And all manufacturers of pump performance data will publish the net positive suction head required by a pump. So that's how you find it. That's pretty easy and straightforward. Now,
Two questions.
yes.
Well, one, yeah, isn't ice water in a different state?
Ice water?
I think she's referring. Well, anyways, that's a joke.
Oh, it could be in Alaska.
Yeah,
Alaska's a different state, isn't it?
yeah, Heidi's making a joke, I'm thinking. But the other question is that a tested value by pump manufacturers?
Yes. So they have to actually put the pump in the test lab and run it through a series of tests in order to determine the required net positive suction head. Isn't that cool?
Nice.
Nice. Okay. So I have this little picture here to remind me of something I'm going to sketch on the screen here. So here's my blank screen. And what I'm going to do is draw a little pot. There's a pot. How do you like that pot, Brett?
Nice pot.
And so the rule is right now we are at sea level. So I'm going to write that up here, sea level. Whoops. That kind of screwed up, didn't it? Well, let's try
No,
this again.
I thought it looked pretty good.
C-A-L-E-V-E-L. There's sea level. And here's our pot one more time. And our pot is open at the top. So it's open to the atmosphere. And by the way, 1 atmosphere at sea level, 1 ATM, not automatic telemachine, but 1 atmosphere, is equal to approximately 14.7 pounds per square inch absolute. So if I fill this pot partially with water, so fill it up here a little, I'm going to call that water, and the water happens to be at 100 degrees Fahrenheit. Now, if I want that water to boil, I would have to, one way of getting it to boil is to add some heat. So let's put some heat in there. And for those that are in the audience, maybe someone could write down in the answer section.
Who's going to be first? Who's going to be first?
Who's going to be first? What temperature do I have to raise that water to in degrees Fahrenheit in order to get it to boil at sea level? Does anybody know what that number is?
Well,
the
first answer was 230 by Lewis, but the second one was Chris at 212. We got Chris, Paul, Chris, another Chris, Robert, Neil, 212. A lot of 212s
212.
here.
So let's just make a note of that. We'll put 212, and that's correct. By the way, that's in the that's in degrees Fahrenheit. If it was in the Celsius, it would be 100 degrees Celsius.
Actually, Heidi did put an F next to her 212.
Nice. Okay, so let's try. Now we can get this water to boil by getting rid of the heat for a moment. So let's get rid of the heat over here. So we're not going to raise the temperature to 212 degrees, but we are going to put a top on our, whoops. Oh, Brett, my thing disappeared.
There goes your water. Your water's leaving.
My water's leaving. Let's try to put my pot back. Okay, here's my pot. There we go. Okay, so I can get this water to boil by doing something different here. I can seal off this pot. So now it's sealed from the atmosphere.
So you brought the pot to our welding products division in Fall River, and they welded it.
They could weld the top on.
There you go.
And then I'm going to have an imaginary vacuum pump. I'll just label this here as vacuum pump over here. And I'm going to evacuate the air that's inside this container until my pressure over here starts to fall. And the question is, how much pressure would I have to, what pressure would I have to reduce this pot to in order to get it to start to boil? Well, it turns out that if I can reduce the pressure to 0.94924 pounds per square inch absolute, that water will begin to boil. So I'll put little bubbles in here representing boiling water. Isn't that cool?
So without the top, at sea level, the pressure is 14.7. And then once you put the cover on and the vapor pot, you got to take a lot of air out of there to get it down that low then, right?
Yeah, exactly.
Yep.
So just to make sure that everyone is comfortable with that number, I think I have it. Let's see if I have it on the chart. Yeah, here is a page from the steam tables. And this is one of the handouts. So in the steam tables, you can see they start at 32 degrees over here.
Yep.
And then it goes up and up from there. But if I go to the next page, I have it highlighted. There's 100 degrees Fahrenheit. That's that first line right there. So that's 100 degrees Fahrenheit. I'll just kind of emphasize that. And there's the pressure, the vapor pressure. So I'm just going to go back to the previous so you can see the heading. So the temperature is in degrees Fahrenheit. There's the temperature. And there's the absolute pressure, which is known as the vapor pressure. And that's the pressure at which the water will begin to boil. So you can see on the next sheet at 100 degrees Fahrenheit, that's where I got that number from the steam tables, 0.94924 pounds per square inch absolute. So if I can reduce the pressure in my container down to that pressure, that water will begin to boil. Isn't that cool? Now at 100 degrees Fahrenheit, what's important to recognize is that I have not changed the temperature this time, I've just changed the pressure. And by the way, I won't spend time doing the derivation, but it turns out that 14.7 pounds per square inch absolute is also approximately equal to 33.9 feet of water column absolute pressure. And if I multiply 14.7 times 2.31, that would be feet per PSI, and that's where that conversion comes from. So if I multiply this 0.94924 times 2.31 feet per PSI, then that's going to be equal to approximately 2.2 feet of water column absolute pressure. Isn't that cool?
That's some heavy duty math right there, baby.
Yeah, that's some cool stuff. Okay, so hopefully everybody got the general concept here is that water will boil not only at 212 degrees if we happen to be at sea level by raising the temperature to 212 degrees Fahrenheit, but if we reduce the pressure inside our container and we happen to start at 100 degrees Fahrenheit, if the pressure gets low enough, in this case it gets to 0.94924 pounds per square inch absolute, and we got that value from the steam tables that were published by someone else, then the water will begin to boil. And that, again, one more time, is called the vapor pressure. Any questions before we go on to the next piece, Brett? Brett, did I lose you? Because I didn't
Question
hear
clear.
any.
No clear.
No questions.
No questions.
Okay. I do want to point out, though, by the way, that when the water boils, it creates these bubbles. And sometimes we can refer to those bubbles as holes. And if you go to the dentist, whenever I go to the dentist, the first thing that the dentist does during his initial examination, he's looking for holes in my teeth, but he calls them cavities, I-E-S. So just kind of keep that name of the holes in the boiling water as cavities. We're going to come back to that use of that word in a minute. Okay, so moving on, here again, one more time, is the copy of the page in the steam tables that has the temperature in degrees Fahrenheit and the absolute pressure. And again, that absolute pressure is the vapor pressure. And then if we look carefully at it, we'll see that the 100 degrees has a vapor pressure of 0.94924. And that's equal to, again, one more time, 2.2 feet of water column absolute pressure. Those are the units. Okay.
Actually, somebody does have a simple. Well, how does elevation affect this? You're very conscious to say sea level, but what if I'm in Denver?
Well, it turns out that Denver is approximately, I'm glad they asked that question. Denver is approximately 7,000 feet above sea level. They call it the Mile High City, but it's pretty close. So it turns out I added this little guy in there, and you can see this little calculator. See the blue lettering at the bottom of the screen here, Brett?
I do.
That's a link. If I click on that link, this little calculator pops up, and I just did a quick screen capture here. And you can see that the pressure at sea level is 14.7 approximately pounds per square inch. and that's at 59 degrees. And if we had an air pressure of 11.34 psi, that would be at 7,000 feet. So the one on the right's a little bit easier to use. If I had 14.7 psi at sea level, and I wanted to go to Denver, which is approximately 7,000 feet, I would click on this calculate button, and my pressure for Denver would be approximately 11.34, the vapor pressure, instead of 14.7. So 11.34, if I could go to my tables for a moment, let's see, can I do this without messing this up? I can keep that.
Uh-oh.
Let's see if I can do this, Brett, without really messing this up. So this is Taco Tuesday, and I had my Steam tables in here. Yeah, there they are. So we're interested in, can you see that table okay?
Yep.
All
I
right,
mean,
so we're
it's small. Oh, see it good now.
yeah, so I'm gonna go down here until I get to absolute pressure. What did I say? Approximately
11
11.34.
something. Yeah.
Yeah, so keep going down, looking for approximately 11.3. So there it's 11.5. So the pressure on this chart, excuse me, I'm sorry, the temperature at which the water will boil on this chart is somewhere between 195 and 200 degrees Fahrenheit, because this is 11.5 at 200 and 10.386 at 195. So the vapor pressure in Denver, Colorado would be approximately 11.34 at 7,000 feet. And then the water would boil at a lower temperature. In this case, we're going to round it off and say it's approximately 197 pounds. Is that pretty close? That's pretty
Yes, sir.
Okay. So hopefully that answers that question. So the higher the elevation, the lower pressure, and the lower the water temperature will be for boiling.
I
And that's
guess the
kind of
moral of the
important.
story is be conscious of elevation, especially when you get up there in elevation.
Yeah, exactly. So if we go, if we, let's see, can we do that? Let's try it. Let's see what happens. If we click on this little, well, let's see, we press this button here, we bring the screen back, and I click on this link. There's the little calculator. Isn't that cool?
Nice.
So you can, you can do a screenshot if you like, or if you get the recording tomorrow, you can easily use this calculator. I thought it was a really cool calculator.
Nice. They got the slides so they can type it in.
Yeah, exactly. Okay, let's try the next slide here. All right, so now let's talk a little bit about how we would calculate what is known as the net positive suction head available. So let's just go one more time and say the net positive suction head, put a little cloud around it, NPSH, which is what's required by the pump. And we showed you how to get that from the pump curve. And what we want to make sure of is that the net positive suction head that's available is greater than what's required by the pump, because if it's not, the water will boil and that will cause the pump to cavitate.
A is greater than R. Think
Yeah,
of the
so
alphabet.
what we want to happen is we want the NPSH available always to be greater than the NPSH required by the pump. Well, that's the important key value there. All right, so we use this equation over here, and hopefully it's large enough for everyone to see. The net positive suction head available is equal to the atmospheric head plus or minus the vertical distance. Now we use the vertical distance, in this case, is 5 feet. And when the water level is 5 feet above the center line of the pump, then we consider that to be a positive value for our H sub Z. And then we subtract the friction head, and then the velocity head, and then the vapor pressure head. So let's plug in some values. Let's see if we can get some values here. And down here where it says net positive suction head available is atmospheric pressure. That's the 33.9 that we talked about. So I'm going to kind of put a little arrow. Whoops, sorry about that. I meant to shut off my phone and I forgot to shut that off today. All right. So the next value is the vertical distance. That's the distance between the center line of the pump and the water level inside the open cell cooling tower. The important thing to keep in mind, this is an open cell cooling tower. And that happens to be 5 feet. And since the water level is above the pump, that's a positive value. If the water level was below the pump, that would be a negative value. By the way, we never recommend that you put a pump above the water level. That never works out well. And then say the pressure drop in the piping system, we estimate that to be approximately 5 feet. And then we want to calculate the velocity pressure. And if I calculate the velocity pressure, that's based on the velocity. And in this case, the velocity is 10 feet per second. So the velocity pressure, and I'll show you where that comes from, is approximately 1.6. So we're going to subtract that. And then we're going to subtract the vapor pressure, which we said was 2.2 feet. And if we do the arithmetic correctly, it's just a matter of adding and subtracting, then we should get this nice little value right here, which is approximately 30.1 feet. And this particular pump that I have for this calculation has a net positive suction requirement of 18 feet. So in this case, the NPSH available is in fact greater than the NPSH required by the pump. So what's available? I'm going to round this off. It's approximately 30 feet. And what's required by the pump is greater than 18. NPSH required. And this is the NPSH available over here. So how much do I actually have? I've got 30 available and I've got 18 required. So I have 12 feet more than what I need, so which is a nice safety margin. All right. So that's how we calculate that. And the whole purpose of calculating this value is, again, one more time, is to make sure that the available pressure is greater than the required pressure. And that will keep the water from boiling inside the impeller.
Someone wanted clarification what you meant by open cell cooling tower.
Oh, good question. So this cooling tower right here means that the water level, I kind of put a little red line in there to represent the water level. This is an open cell cooling tower, which means that the water inside the basin of the cooling tower is open to the atmosphere. So if there was a door over here, here's a little door. I'm going to open the door. There's a doorknob. I open the door and I can actually see the water level inside the tank. If this was a closed cell cooling tower, then the water that's inside the cooling tower that's circulating back to the chiller would be closed off from the atmosphere, and that would be a pressurized system. So generally speaking, the issue comes up when we are trying to deal with vapor pressure associated with the atmospheric pressure. Now, if this was, again, in Denver, Colorado, then instead of using 14.7, we'd have to use something like 33.4, and we'd convert that into, I'm sorry, 13, did I say 33? I should have said, let's go back and see what the actual value is back here. 11.34, sorry, pounds per square inch. Okay.
So we have a couple of, we have a question and a statement.
Okay.
Typically known as a fluid cooler as opposed to an open tower. So I think that was part of the closed open tower conversation you were discussing.
Yeah, a fluid cooler is generally known in the industry as a closed cell tower. Fluid cooler is not open to the atmosphere.
Here's a great question right here. How much of an NPSHA safety margin should you design for?
I like to design for 10 feet safety factor. Now, some engineers will design to 5 feet. I'm somewhat conservative. I like to do 10 feet if I can get away with it.
I like to make a statement when I look at this drawing here. And for many, many projects that I've been involved in, that dimension of 5 feet that Rich shows from the center line, or where the water comes out of the tower to the center line of the pump, many projects, that dimension if you think about a tower up on the roof, I'm at our facility in Cranston, Rhode Island, right? And we have our tower up on the roof. The pumps, so we have more than one, but anyways, backup and stuff are down in a mechanical room, and the distance is probably 60 feet. So on many projects for many years, this really was a um, a calculation that may have been put on the back burner. And I'm only making this statement because Rich and I and others at our company, and I think others in the industry are starting to see a lot different setups on projects now. You know, they don't want to put the tower on the roof. Canada, they put it down lower. They did this and that. So I'm only making these statements because please, at least consider the numbers. Personally, I would do the calculations or have a junior engineer that's in for the summer do the calculations and teach them, but really consider it. It's something that really can't get overlooked anymore. How does this calculation get affected if specifying a pump in a closed loop system? That's a good question by Khalid.
Yeah, so let's go back to the discussion screen. There's our discussion. So it turns out that if it's a closed loop system, in most closed loop systems, if not all, but there are exceptions, always exceptions, the pressure in the system is controlled by in combination with the fill valve and the expansion tank, and they work in concert with each other. And so the expansion tank is connected to the suction side of the pump. That's the preferred location. That's called a point of no pressure change. And in that circumstance, since you can add pressure to the suction side of the pump, generally speaking, you can add enough pressure so that you don't run into this cavitation issue when the available pressure is less than the required pressure. So let me see if I can, let's see, discard. I want to go back here one more time because I wanted to show something. Well, let me do this. And any other questions, Brett? Because I wanted to.
Yeah. Go back to your little sketch there.
The one with the tank.
The one with the no, the one with the tower and the pump and
Oh,
the
yeah,
5
yeah.
feet and all that. Yeah.
This little diagram here.
Yeah, this is actually a great point by Mark. What about a strainer? The pressure drop through a basket strainer can be pretty darn high, and the published data often underestimates the true clean and loaded pressure drop. I've had to oversize these. Be careful with basket strainers, right? Or strainers of any type, I think is probably the best statement there.
Yeah, no, you're absolutely right. Let me do something. I want to do something a little goofy here. There we go. And get rid of this statement up here. Oh, look at that. Okay. I just wanted to have another sheet to draw on here. But do we have any other questions before I dive into one other little sketch I wanted to make?
A couple of people have made the statement that cavitation sounds like the pump is chewing gravel.
Yeah,
I kind of like that.
Cavitation is generally, most people notice that a pump is cavitating or potentially cavitating. Let's use the word potentially, because it's making a noise like it's pumping rocks or marbles, or some people say ball bearings, that kind of stuff like that. It's really loud.
And the bigger the pump, the louder it is. And
the louder it is, right.
And the quicker that pump is going to be destroyed. Simple as it's simple as that.
So I'm going to draw a cross section. Here's a little cross section of an impeller. It's diagrammatic, so kind of bear with me here. This dotted line represents the vanes that are inside the impeller. There's the vanes. The water flow is from left to right. This is the inlet right here. There's the inlet. So I'll call that the inlet of the impeller, sometimes referred to as the eye, E-Y-E. Let's assume that the water temperature is 100 degrees Fahrenheit, like our little example, and the pressure happens to be approximately 2.2 feet. And again, that's feet of water column absolute pressure. Well, what happens is when the water actually flows from the eye or the inlet in the impeller to the discharge side of the vanes, like this, the pressure increases along that traveling path. And when the pressure increases, those little bubbles that were forming at the inlet of the impeller right here, they collapse. It doesn't take much distance for them to start collapsing. And when they collapse, they create a shock wave, and that shock wave eats away, literally takes chunks out of the veins of the impeller. It'll eventually destroy the impeller. So that's the main reason why we want to keep the pressure high enough for a given temperature so that it doesn't form initially bubbles and they collapse. And that collapsing action, that phenomenon, is called cavitation. Cavitation, there we go. Cavitation is the phenomenon of collapsing bubbles as it moves from the inlet to the outlet of the impeller. I like that sketch, Brett. That was kind of nice.
Yeah, that is a good one. That's a good one.
So do we have any other questions floating around?
Yeah, can you go back to your sketch of the the tower and the calculation?
Yeah, this tower here.
Someone asked how you calculated the 1.6 feet.
Oh, okay. Yeah, that's a cool one. So let me go down here to my diagram, and can I erase this?
Yep. Well, I think you have the ability to.
I can. If I erase it, it's going to go away. Hopefully everyone sees that. If not, I may have to redraw it again. So I'm going to erase that. Whoops. Yeah. I meant to erase the whole thing. There we go. Okay, so the velocity head, sometimes referred to as h sub v, is equal to the velocity squared divided by 2 times the gravitational constant. And the velocity has to be in feet. For imperial units, the velocity has to be in feet per second. And the gravitational constant for imperial units is 32.2 feet per second squared. And that's the acceleration of gravity. So if I substitute, let's assume that I had a velocity of v of equal to 8 feet per second, FPS. Let's keep that in mind. So whoops, I didn't want to make a V there, Brett. Oh, I cannot erase. Oh, it's so depressing when you can't erase what you want to erase. now my thing is like, it's like fighting me every inch of the way here. There's my eraser.
There you go.
Okay, I got my eraser.
Just don't run your fingernails down the chalkboard, please.
I try not to. Okay. All right. So let's see the velocity head. So now we need a pen. The technology is a wonderful thing. Okay, we've got our pen back. Okay, so the velocity head, if you kind of give me a little poetic license, is equal to the velocity in this case is 8 feet per second, and that whole thing is squared, divided by 2 times the gravitational constant, which is 32. Let me put this in parentheses, times 32.2, and that's feet per second squared. So if I rewrite this one more time, the velocity head is equal to, say, 8 squared is 64. So the units are going to be 64 feet squared per second squared, divided by, well, 2 times 32.2 is 64.4. But for this example, I'm just going to round it off and round it down a little bit, and you'll see where I'm headed in a minute. So I know it's not the exact value, but I'm going to put it in here as 64, and that's going to be feet per second squared. So the second squared cancels down here, feet cancel, the square cancels up here, and the velocity head is equal to approximately 1 foot. Isn't that convenient? Look at how nice that works out.
Nice.
And
so your
1.6
came because it was 10.
Yeah, exactly. So if I use 10 and I did that calculation, hopefully somebody's got a calculator. Let's do it together. Obviously 10 squared is 100 divided by 64.4 comes out to 1.55, and I used 1.6. Is that everybody okay with that?
Yep, and great point by you. You got to be careful with that velocity. You don't want to go too high or too low. 8 feet per second or lower is probably standard for most systems. But if you go too low, you can have issues, and if you go too high, you can have issues with the piping and stuff like that. Good
Yeah, I
comment
mean,
there.
we try to get as close to 8 feet per second, especially on an open cell cooling tower at the inlet of the pump. We don't want to be much higher than that. In our example, like you said, we were using 10 feet per second, and that's where the 1.6 came from.
In a closed loop system, would we discard the elevation difference?
In a closed loop system, the elevation is not in consideration because you're controlling the pressure in the system via the fill valve and the expansion tank. So you become the master of the pressure.
Run the calc is Henry says, can you run the calculation if the water temperature is 160?
Yes. The only thing that changes in that calculation, let's see if it goes back to the previous sheet. The only thing that changes at 160 degrees instead of 100 degrees is the vapor pressure. So we'd have to go back to the steam tables. Let's go back to the steam tables. Well, I'm gonna have to go to my other sheet where I had the steam tables. Let's discard that for a minute. And I think the steam tables I have, where did I have that, Brett? I had that opened earlier.
You had them open, but I don't know where the hell you had them. Oops, where the heck you had them?
I think I have it here. Here it is here. So at 160 degrees, we would use, here's 160 degrees. There's 4.7414. So if the water temperature was 160, it would be 4.7414. And 4.7414 times 2.31. Then our vapor pressure would be approximately 10.9, almost 11 feet. So it has a significant impact. So when you go back to the equation that we used, instead of subtracting 2.2, see, can we go back to the slide? Yes, we can. Instead of subtracting 2.2 down here for the vapor pressure, you'd be subtracting approximately 11 over here at 160 degrees.
Probably at 100, most systems that are open wouldn't have a temperature that high. You know what I mean? I mean, even if
It's
you're in
possible.
Vegas
I
with a,
mean, some systems, especially special types of hot water systems,
yeah,
will dump into an open tank. But usually the water temperatures, as you said, Brett, it's usually not that high. But for the open systems that we see that are using hot water, it's usually a process system. They generally don't have temperatures much above 160 to 180. Because again, if you start getting close to 212 and you're at sea level, that water is going to boil away.
right. Well, I don't see any more questions. Let's see. What can I think of? Like I said, please really consider it on every project. I mean, Rich can give you some great examples, and from my perspective, it's never a 5 or 10 horse pump. It's usually a 50 to 200 horse pump where there's a problem, and then there's more than one pump or whatever, and it really becomes an issue.
Here are some pictures. Can you still see my screen okay?
Yes, sir.
I just typed in cavitation impeller in the Google search, and if you'll notice, look at these different impellers that have been eaten away because the pump was cavitating. Look at
It's
this
not
one
just
over
the
here.
impeller either. It's the whole
Yeah, the
pump. I
casing
mean,
can
the
also
wet end's
away.
going to get destroyed as well.
It's dramatic. It's amazing. Yeah. Some of these pictures online. Here's one. Here's only, look at this thing. It looks like Swiss cheese. Completely destroyed. And here's one over here on the right. There's another one.
Yeah.
Here's one of my favorites. This one here. I like that one.
Yeah.
So yeah, it'll destroy an impeller, eat away at it. It looks like somebody got in there with monster bugs and started chewing away at the metal.
All right, we got a couple more questions that came up.
Okay.
How do the calculations change if you have multiple pumps in parallel? Can you still hear me, Rich?
I can.
Okay. How do the calculations change if you have multiple pumps in parallel?
Well, the calculation doesn't change. What changes is where the pump is operating on its curve. So for example, let's do a quick pump selection. Let's see if we can get this to work here. Pump selection, let's see, Taco HVAC, pumps and circulators. All right, we're going to use the selection tool here. I'm going to go rather quickly because we want to see what parallel pumping looks like. And let's just arbitrarily make a pump selection at 500 gallons per minute.
This is a little preview of our next, in 2 weeks, we're doing this. Pump selections
Pump
with the
selection.
software.
Look at
Oh
that.
my God.
Oh my God. Let's make 80 feet here. Let's make it 2,000, just 2,000 for the fun of it. Click on more down here, and I change the number of pumps from 1 to 2. And then I'm just going to make a quick selection here for KS pump. I happen to like KS today. I like KS all the time. That's a vertical inline pump. So the software is going to come back and it's going to make a couple of recommendations, and we're going to look at this. See these little road signs here that says rated head above maximum pellet diameter? That's a warning, and that's called a near miss. So I can click over here and get rid of the near misses and just look at the 6011D. Actually, before I do that, I'm going to go back to results again one more time. Because if I hover over here, I can kind of see the system curve and the pump curve. I'm looking for one that might be a problem here. This one looks like it could be a problem. This is definitely a problem. All right, so that's the 1013A. Let's look at the first one here. The first one shows that if you have both pumps operating, you'll see you have this nice smooth curve over here. That's with both pumps operating. And then this dotted line is when only one pump is operating in a parallel pumping system. In both situations, whether you have two pumps or one pump, they cross the original system curve line here. And so you run into a problem if we go back and we look at one of the other pumps. It's not one that I would recommend selecting, but we want to show it to exaggerate for a moment. Here we have two pumps operating in parallel. That's the solid blue line, and that's running okay. But look what happens if you run one pump. If you run one pump, you're way at the end of the pump. You're off the end of the pump, and your NPSH begins to take off. Because if I notice back here, my NPSH, let's say if I was running the pump, say more toward the left here, around 500 gallons per minute, let's just pick that. The NPSH required for that single pump operation would be approximately, let's see, what have I got here? Oh, it's not displaying it. Well, isn't that weird, Brett?
Yeah.
Well, we can read it on the chart. You can see that the NPSH at the bottom of the curve here, it looks like it's about an average value of around 20, maybe. That looks close, around 20 feet. But if I get to the end of the pump, you can see that the NPSH at the top of the chart here begins to take off, and now it's much higher. It's getting up there around that value right there. It's getting to be about, let's see, halfway between 25 and 50. That's another 25, 12. So it's about 37 feet. So from the minimum pressure around 23 to 37, that's a significant difference. And so when you run one pump in a parallel system and you happen to run off the end of the curve, that could be a potential problem for you. Where two pumps operating are going to have a relatively low NPSH. In this case, it's around 30 feet. But one pump operating, it's going to have a number that's probably higher than that, maybe up to 40 feet, that sort of thing. So hopefully that answered that question.
Yep. So go back to, yeah, this sketch right here. Here's a great question that, we talk about it and stuff like that. So you estimated 5 feet of pressure drop. What is a typical friction value in suction piping? Besides strainer and valves, what else should be concluded in this number?
Well, I don't like to use the typical value. I prefer to say you need to do a detailed pressure drop calculation from the connection of the cooling tower to the inlet of the pump, because it could be a variety of situations. I ran into a situation not too long ago where the owner of the building had planned initially to put the cooling tower on the roof. You ready for this, Brett?
Yeah.
Put it on the roof of the parking garage, which was adjacent to the building. And the parking garage was 5 stories tall. Well, that was great, right? Because the parking garage was about 12-foot floor to floor height, 60 feet in the air. The cooling tower was like 65 feet above the center line of the pump. Well, in the last few days of construction, literally in the last month, I think, of construction, before the cooling tower was delivered, the owner said, I can't put the cooling tower on top of the garage anymore. I have to put it on grade.
Oh boy.
And to make things even worse, rather than being adjacent to the mechanical room, they had to put the cooling tower 1,000 feet away. So you can see that the distance of the piping and the elbows and the fittings and stuff had a huge influence. When we did the calculation, well, the engineer of record did the calculation. We guided them through it. It turns out that the available pressure was something like 5 feet, and the required pressure of the pump was like 30 feet. So it was a real disaster. So rather than say typical, my recommendation is to do a detailed pressure drop calculation between the connection of the open cell cooling tower and the center line, the suction flange of the pump. That's a critical calculation, and I don't like to put a typical value on there.
So Michael's saying often the pump suction in a short inlet pipe is smaller than the system piping. That would increase the velocity right at the inlet. Does that mess up the calc?
No, because
Careful.
remember the velocity head that you're calculating, in this case 10 feet per second on this diagram, is calculated at the pump size. So in other words, if it was a smaller size, you would calculate it based on the velocity of the smaller size connection on the pump.
We're pretty much done.
It sounds
All right,
like
wait
we
a minute.
had some great
For
questions.
for a new installation, do you recommend using NPSH formula, where HA is atmospheric pressure at the fluid temperature and HF is the friction and head loss from the fluid source to the pump inlet? I guess.
I'm not sure I understand the question.
Yeah.
Try it one more time.
For a new installation, do you recommend using the NPSHA formula? Yeah.
Yes.
Why wouldn't you?
Yep.
Yeah. I would use that formula all the time.
Yes.
Well, how does glycol affect the system? The calc?
Well, if it's an open cell cooling tower, you would not use glycol in the cooling tower.
Bingo, bango, bongo.
If it was a closed cell, a closed system, closed pressurized system, you would use glycol, and then you would look up the vapor pressure for glycol to see if it's going to. Generally speaking, if it's glycol, the vapor pressure is not going to have a huge impact because you're pressurizing the system similar to just straight water.
Yep. He says, are there pumps with very small NPSHRs?
Yes, you can actually find pumps that are relatively low. Sometimes, let's go back to our pump selection for a moment, just for the fun of it. Let's go to a single pump selection. We got, I'm going to go to 1,000 gallons per minute here and have a single pump. Sometimes, if you notice, I have a KS pump here. I'm going to also have an HS pump. An HS pump uses a double suction impeller, which means that when the water enters the impeller, it splits and the flow goes, half the flow goes to the front half of the impeller and the other half goes to the back half of the impeller. So the velocity at the inlet is at the impeller rather is lower, in which case the pressure is slightly higher. So if you'll notice, if I sort by NPSH from lowest to highest, you'll see that in this particular case, well, it turned out the KS was actually lower in this particular configuration.
That's because
But
that one probably has a double suction too.
it may, yeah, because of its size. But one of the interesting things here, for example, so here is an HS pump that has 14.5, and then one at the bottom of the list, this KS, has 30. So in other words, if your original selection was this KS 5007, you can see that that would have an NPSH of 30.2 feet, and this one over here, which would be an HS, 14.5 feet. So yeah, they can vary quite dramatically.
That's pretty much it, Rich. I think we're done.
Well, that sounds like we've covered a lot of material. Thank you, folks, for hanging in there and listening to our lecture, and also the great questions today.
Yeah. Like, I think I forgot to mention with all the excitement up front, there will be a recording. This was recorded, so you'll get a copy of that tomorrow, roughly 24 hours after now, and access to your one PDH certificate. If you ever have issues with either of those, let us know and we will track them down. Other than that, Rich, say goodbye and then I'll say goodbye.
Yeah, so again, one more time, thanks so much, everyone, for participating in today's discussion. We had some great questions, and we look forward to seeing what is it, the next one in roughly 2 weeks, Brett?
2 weeks, yeah. What's today? Today's the 6th of May, so 14 and 6 is 20. Is
Wow.
that still true? I think that's still true. You know, me and long math gets difficult sometimes, but
Yeah, I can't do math anymore. I can
point
do grocery bills.
0.94924. You know that number pretty good though.
Yeah, I memorized that puppy.
Thanks, Rich. Great job, everybody. Great questions. We will see you in a couple of weeks. Take care. Bye
Take
now.
care, folks.